Welcome to this ground lesson on the principles of flight. In this session, we're going to dive into the core concepts that explain how and why airplanes fly. We'll walk through aerodynamics, the forces acting on an aircraft, airfoil design, aircraft stability, and much more. Whether you're preparing for your knowledge exam or brushing up on fundamentals as a pilot, these principles are important for safe and efficient flying. This lesson is based on the FAA's Airplane Flying Handbook and the Pilot's Handbook of Aeronautical Knowledge. Let's get started. Let's begin with the big picture. Why do we need to understand the principles of flight? As pilots, we don't just operate an aircraft. We manage its performance, interpret its behavior, and respond to its limitations. To do that well, we need a solid understanding of the forces acting on the airplane, how we can use them to our advantage, and how they can also become limitations if we don't handle them properly. At the core, an airplane flies because of lift, primarily generated by the wings. That lift is explained by two key principles: the Bernoulli's principle and the Newton's third law of motion. To leverage these principles, the wing has a distinct cross-section shape called airfoil. Let's learn more about it in the next slide. Now let's take a closer look at the basics of aerodynamics, specifically how air behaves around the aircraft. Starting with Bernoulli's principle. This says that as the speed of airflow increases along a surface, the static pressure at that surface decreases. This can be proven by blowing air through a venturi. As the air gets squeezed through the venturi, the speed of the fluid in that section increases, causing the static pressure on the walls to decrease. With that same principle, as air accelerates over a curved surface like the top of a wing, the pressure drops. That pressure difference between the upper and lower surfaces of an airfoil generates lift. The second principle is Newton's third law. For every action, there's an equal and opposite reaction. As the wing deflects air downward, the equal and opposite reaction is an upward force on the wing. This means that as the wing pushes air down, the reaction force pushes the wing up. These ideas are foundational for understanding not just wings and lift, but also propellers, carburetors, and even instrument systems in some aircraft. Let's now look at how different aerodynamic forces interact with the wing and affect flight. Take a look at the airfoil picture at the bottom of this slide. The arrow labeled relative wind shows the direction the wind is coming from, taking the airfoil as reference. As the relative wind hits the airfoil, there will be an upward and slight backwards force generated by it. We call this resultant force. Here's where we start defining things. We can split that resultant force in two components. One that is parallel to the relative wind and one that is perpendicular to the relative wind. Let's call them lift and induced drag. Lift is the force that acts perpendicular to the relative wind. Induced drag is the force parallel to the relative wind and is always trying to slow us down. We use the term induced because that drag is a byproduct of the lift. We will learn more about different types of drag later in this lesson, so for now, let's focus only on lift. Lift is influenced by several factors. Let's break that down. First, angle of attack. The angle of attack is the angle between the relative wind and the chord line of the airfoil. Okay, but what is chord line? Well, chord line is an imaginary line that connects the leading edge to the trailing edge of an airfoil. As we increase the angle of attack, lift and induced drag increase. This doesn't go forever, though. At some point, and that's what we call critical angle of attack, the airflow will detach from the airfoil surface, lift will be lost, and we will have an aerodynamic stall. So here's an important lesson. An aerodynamic stall can happen at any airspeed. It can happen while climbing, while descending, in cruise flight, etc. Whenever the critical angle of attack is reached, the wing will stall. Some aircraft have indicators for angle of attack, but since most don't, manufacturers publish stall speeds, which is just a way to indicate, from test flight, what airspeed the aircraft reaches the critical angle of attack in wings level flight. Okay, let's go back to the factors impacting lift. The second one I want to talk about is airspeed. Lift increases with the square of airspeed. So doubling your speed can quadruple lift. You can use these two variables, airspeed and angle of attack, to control how your airplane flies. Let's say your engine power is constant, unchanged, and you start to increase your angle of attack. As you are doing that, you are increasing lift, but you are also increasing induced drag. As you continue to increase the angle of attack, your airplane starts then to slow down because of the induced drag that is being increased. With the airplane slowing down, the reduction in airspeed then reduces lift. Thing eventually will fall into an equilibrium, and that's what we will cover in the next slide. There are four fundamental forces acting on an airplane in flight. Lift, the upward force created by the wings. Weight, which is the weight of the aircraft. It points down and can be represented by a single force acting through the aircraft's center of gravity. Thrust, the forward force produced by the propeller. And drag, the backward resistance that slows the airplane down. Drag can be broken down into two major types. First, induced drag, which we discussed earlier. Second, there is the parasite drag. The parasite drag exists because of the shape of the aircraft, called form drag, also because of the interference of airflow across different components of the airplane, such as where the wings meet the fuselage. We call it interference drag, and also because of the air friction with the airplane skin, and we call it skin friction. The combination of the parasite drag with the induced drag gives us the total drag of the airplane. Now you know the four fundamental forces. In a level flight, the airplane reaches equilibrium when the lift is just enough to counter the weight, and thrust is just enough to counter drag. The sum of all forces is zero, and the airplane is in constant airspeed and constant altitude. When climbing, for example, the weight of the airplane continues pointing downwards. So we need to split it into two components, one that is parallel to drag and another that is parallel to lift. In that scenario, the lift must be enough to counter that component of the weight. The thrust must be increased, because now it needs to offset not only the drag, but also the longitudinal component of the weight. That's why we say that an airplane climbs when there is excess thrust. When all forces are in equilibrium, the airplane is then climbing at constant speed and constant climb rate. I know this can be confusing if you are learning this for the first time, but bear with me as there is one last topic I want to cover, and that's the best glide speed. Look at the chart at the bottom of the slide. This shows the relationship between induced drag and parasite drag. Here's how it works. As the airplane increases airspeed, lift is increased, so you can reduce the angle of attack to maintain lift constant and remain in the same altitude. As you decrease angle of attack, the induced drag then decreases. However, as you increase airspeed, the parasite drag increases. There is then an optimum airspeed where the total drag is minimum. Considering that we are maintaining the lift constant throughout all the different airspeeds, if you fly at that point where the total drag is minimum, we will have the highest ratio between lift and drag. That is called best glide speed, and it is published by the aircraft manufacturer. It is important to know that because that's the airspeed you want to fly in case of an engine-out emergency, for example, where you want to maximize your glide range and increase your options for a landing location. Let's talk about a special aerodynamic phenomenon that pilots must be mindful of near the ground: the ground effect. When an airplane is flying, the pressure at the top of the wing is lower than the pressure at the bottom of the wing. This pressure differential causes the wing to lift up. However, at the tip of the wing, the air tends to migrate from the bottom to the top of the wing, taking a shortcut outside of the wing. This causes wingtip vortices, which disturbs the airflow around the wing, reducing lift and increasing drag. This makes the wing less efficient. However, when the airplane is close to the ground, more precisely less than half wingspan above the surface, the proximity to the ground interferes with the airflow patterns around the wing, disrupting the wingtip vortices and improving the efficiency of the wing. This interference reduces induced drag and effectively increases lift. Pilots should be aware of that and expect this to happen during takeoff and landing. On takeoff, ground effect can trick you into lifting off prematurely before reaching proper flying speed. The airplane may become airborne, but as soon as it leaves ground effect, it may have trouble on climbing. On landing, ground effect can cause the aircraft to float above the runway, requiring more runway to land or leading to a balloon if not managed properly. Let's go back to the airfoil. An airfoil is a cross-sectional shape, like that of a wing or horizontal stabilizer, designed to create lift efficiently. Lift and drag are generated by the pressure differences between the upper and lower surfaces of the airfoil as air flows around it. You already know that at this point. Different airfoil designs suit different aircraft purposes. A glider, for instance, will have a high-lift, low-drag airfoil for efficiency, while a fighter jet may use a thinner airfoil optimized for speed and maneuverability. An aerobatic airplane may have an airfoil where the top and bottom curves are symmetrical, so it can sustain flight even when upside down. A key concept I would like to introduce here is the center of pressure. The center of pressure is the point along the chord line where the total lift force is considered to act. As the angle of attack increases, the center of pressure moves forward, and this has implications for pitch stability. Another concept you should know is the angle of incidence. This is the angle between the chord line and the longitudinal axis of the wing. A wing can be designed using different angle of incidence across the wing span. Designers often reduce the angle at the wingtips compared to the root. Why? This helps the root stall first and keeps ailerons effective during the early stages of a stall, giving you roll control when you need it most. Now let's talk about flaps. Deploying flaps changes the entire shape of the wing. They increase the surface area and camber, which boosts lift, especially at slower speeds. But that also brings more drag, which helps us descend more steeply without picking up speed. Flaps also change the chord line, which means they increase the effective angle of attack, even without pitching the aircraft up. So, when you deploy flaps, you're not just slowing down, you're fundamentally changing how your wing performs. For example, when you are coming to land and deploy flaps, your angle of attack increases without the need to pitch the aircraft up. This increases drag, reduces airspeed, and increases lift. It also helps with visibility, since you don't need to pitch up to increase the angle of attack. Next, let's look at the wing planform. The shape of the wing is viewed from above. This design choice affects everything from lift and drag to stall behavior and structural efficiency. Key factors in wing planform include aspect ratio. This is the ratio of wingspan to average chord. A high aspect ratio wing, like on a glider, reduces drag and increases efficiency. Low aspect ratio wings, like on fighters, offer strength and maneuverability but more induced drag. Taper. This is when the chord narrows from root to tip. A tapered wing is more efficient and can delay stall at the tips. Sweepback. Wings that angle back, common in high-speed jets, help delay the formation of shock waves and reduce wave drag at transonic speeds. They also contribute to lateral stability, as we'll see later. Each wing planform is a compromise. Designers balance lift, speed, efficiency, stability, and structural strength to match the aircraft's mission. We usually see regular rectangular wings in training aircraft because it tends to stall from the root to the tip, giving better notice and making it more controllable since the ailerons stall later. Let's now dive into stability and controllability, two foundational concepts in aircraft behavior. Stability refers to the airplane's natural tendency to return to a steady flight condition after being disturbed. There are two types of stability. The first type is called static stability, which is the initial response. If you pitch the nose up and let go, does the aircraft start to correct itself, stay where it is, or keep pitching away? If it starts returning, then you have positive static stability. If it stays in the new pitch, that's then neutral stability. If it worsens and pitch continues to increase, it is called negative static stability. The second type is called dynamic stability, which describes how an aircraft that has positive static stability behaves over time. Does it dampen out the oscillations, or do they increase? The aircraft's stability affects the capacity to control and maneuver the airplane. Here are two important concepts to grasp. The first concept is controllability, how well the aircraft responds to control inputs. This defines the quality of the aircraft to follow desired paths. The second concept is maneuverability. which is the aircraft's ability to change attitude or direction. How fast can they change attitude and direction and still withstand stress? The more stable an airplane is, the less maneuver it is. For example, a transport plane is built to be stable. A fighter jet, not so much. It's designed for aggressive maneuvering with stability augmented by systems. A key factor in stability and control is the center of gravity, or CG. Where the CG is located significantly impacts how the aircraft flies. Let's compare forward and aft CG positions. Starting with a forward CG, the aircraft requires more nose-up elevator force to maintain level flight. That increased elevator deflection requires the tail to push down harder, which translates to more load on the wings. So a higher angle of attack is needed to produce enough lift to counter not just the weight, but the increased elevator load. This results in more induced drag, reducing cruise efficiency. This also increases stall speed. Think about it. The airplane is already flying at a higher angle of attack, so the airplane has less room before it reaches the critical angle of attack. On the upside, stall and spin recovery is easier because the moment arm to the tail is longer, meaning the tail has more leverage to correct pitch, and the forward CG will tend to bring the nose down quicker. Overall, forward CG equals more stable but less maneuverable. Now with an aft CG, the tail needs less downward force, reducing overall wing loading. This results in lower drag, higher cruise speed, and a lower stall speed. Overall, more efficient at cruise. But here's the danger. Pitch stability decreases. Recovery from a stall or spin becomes harder due to the shorter arm between CG and the tail, and between the CG and the center of pressure. Overall, an aft CG can make the airplane less stable and more sensitive to pitch inputs. What we just discussed, forward versus aft CG, is part of what we call longitudinal stability. The longitudinal stability is the stability about the lateral axis, the pitch axis of the aircraft. In a longitudinally stable airplane, if the nose pitches down, the aircraft starts to pick up airspeed, and that increases the downward forces in the elevator, pitching the airplane back up. Three main design factors contribute to this: the location of the wing relative to the CG, the position of the horizontal stabilizer, and the size of the tail surfaces. Larger stabilizers provide greater corrective force and help dampen pitch oscillations. Now let's shift to lateral stability, which is the aircraft's stability around the longitudinal axis, or roll stability. There are three main contributors to lateral stability. Dihedral. This is the upward angle of the wings from root to tip. When the airplane rolls into a side slip, the lower wing has a higher angle of attack, generating more lift and rolling the aircraft back toward level flight. Sweep back. Even a slight sweep of the wings toward the rear improves lateral stability. That's because the lower wing in a side slip presents more surface area to the relative wind, generating more lift and bringing the wing back up. A good rule of thumb is that about 10 degrees of sweepback offers the same stabilizing effect as 1 degree of dihedral. Keel effect and weight. This is especially noticeable in high-wing aircraft. The aircraft behaves like a pendulum. The fuselage mass below the wings resists rolling, helping the aircraft return to upright flight. In practice, you'll feel lateral stability when you release the yoke after a gentle bank and the aircraft slowly rights itself. The last axis of stability is directional stability. This refers to stability around the vertical axis, or yaw stability. Imagine you're flying straight and a crosswind pushes the nose slightly off course. Will the aircraft naturally weather vane back into the relative wind? If yes, it has positive directional stability. Two main features contribute to this. The fuselage area aft of the CG. When the nose yaws, the side of the fuselage acts like a weather vane, helping to push the nose back in line. The vertical stabilizer. It provides the most significant stabilizing force. The larger it is, the stronger the yaw correction. While directional stability helps maintain heading, too much of it can make the airplane resistant to coordinated turns. So again, it's all about balancing the design. Let's talk about the four main left-turning tendencies that pilots experience in an airplane, especially during takeoff and climb. Torque effect. As the engine rotates the propeller clockwise from the pilot's view, Newton's third law tells us The aircraft tends to roll counterclockwise. This causes a left roll tendency, most noticeable during high power and low airspeed, like takeoff or recovery from slow flight. Corkscrew effect, also called spiral slipstream. The rotating propeller produces a spiral flow of air that wraps around the fuselage and hits the left side of the vertical stabilizer, pushing the tail to the right and yawing the nose to the left. P factor. This is the asymmetrical thrust generated by the propeller when the airplane is in a nose-up attitude. The descending blade on the right side takes a larger bite of air, producing more thrust than the ascending blade on the left. This causes a yaw to the left. Again, most noticeable during high power and high AOA. Gyroscopic precession. In tailwheel aircraft, when the tail rises on takeoff, the gyroscopic force of the spinning propeller disc acts 90 degrees ahead in the rotation, creating a yawing moment, usually to the left. In tricycle gear aircraft, this is less of a factor, but can cause a right-turning tendency during abrupt pitch-up if precession is significant. Knowing these tendencies helps you anticipate and correct them, typically with right rudder during takeoff, roll, and climb. Let's now talk about load factor, one of the most important aerodynamic concepts that affects both safety and aircraft performance. Load factor is defined as the ratio of the total aerodynamic load on the aircraft to its weight, and it's measured in Gs. 1 G is equivalent to the force of gravity acting on the airplane in straight and level, unaccelerated flight. But once you start maneuvering, turning, or encountering turbulence, that load increases. The aircraft's structural design is rated for a specific G-load range, depending on its certification category. These limits are illustrated in the VG diagram, which shows the aircraft's maximum G-load versus airspeed. So how exactly does load factor increase in a turn? In straight and level flight, lift equals weight. But when you bank the aircraft, lift is split into two components: a vertical component that opposes gravity and a horizontal component that turns the aircraft. To maintain altitude, the vertical component must still equal the aircraft's weight. That means total lift must increase, which translates in increasing the angle of attack. And that's where load factor comes in. For instance, at 45 degrees of bank, the load factor is about 1.4 Gs. At 60 degrees, it rises to 2 Gs. That increased load also increases the stall speed because the wing is flying at a higher angle of attack. So if the angle of attack increases further, the critical angle will be achieved sooner, at a higher airspeed than level flight. In the beginning of this lesson, we briefly talked about wingtip vortices in the context on ground effect. Whenever an airplane is producing lift, there will be wingtip vortices flowing from the bottom to the top of the wingtip. These vortices continue spiraling downwards, increasing in size in the stream of air behind the aircraft. An airplane flying behind another airplane in the path of their wingtip vortices may experience wake turbulence. The hazard of flying through a wake turbulence is not just the turbulence itself. These vortices can create rolling moments that exceed your control authority, especially for lighter aircraft. The wake turbulence is worse in heavy, clean, and slow aircraft. For example, a Boeing 747 taking off. So how do we protect ourselves from wake turbulence? It comes down to timing, spacing, and awareness. Avoiding wake turbulence is particularly important during approach, landing, and takeoff. Here's the most important things you need to know. If following a large aircraft on approach, stay above its glide path. During an approach in an airport with parallel runways, be alert to vortex drift, especially with crosswinds. If landing behind a departing aircraft, try to land before their rotation point. If landing behind an arriving aircraft, touch down beyond their touchdown point. If another aircraft is performing a missed approach, wait 2 minutes before departing or crossing paths. If departing behind a heavier aircraft, rotate prior to their rotation point and climb above their flight path. Be cautious with intersection takeoffs, as you may not get the same clean air. Again, wait 2 minutes after a large aircraft performs a missed approach. Being aware of where the vortices are likely to be and giving them time to dissipate is critical. These invisible hazards can flip or stall an airplane before you even know what's happening. And that wraps our lesson today. Thanks for watching. And if you like this content, please consider subscribing. This will help us create more lessons like this.